Hi everyone, now we are at Multivariable Calculus, lecture number Maxima and Minima. Okay, Maxima and Minima of functions of several variables, 2 and 3 variables here we are going to discuss. If it is more than 3 variables also we can do it by using Lagrange Multipliers, but here in the syllabus only 2 and 3 variables only by the method Lagrange Multiplier. By using Lagrange Multipliers only we are finding Maxima and Minima. So before entering into maxima minima, we need to know a few little things. First one is critical point. We need to know what is critical point. An interior point of the domain of a function f of x comma y, where both fx and fy are 0, or where one or both of f of x and fx and fy do not exist. It is said to be a critical point or a stationary point of f. What is geometrical meaning of these things? See, I will explain in one dimensional what is meant by this. For example, let us consider this curve. Okay, consider this curve. Now this is f of x. Let us consider for only one dimension. Let us consider this is a curve f of x. Now look at this point. Assume this is a point which is x. At this point x1, let's say it is x1, here the derivative, look at clearly, what is the tangent? This is a tangent, so therefore the tangent is exactly parallel to x-axis. Therefore clearly I can say that f dash at x1 is equal to 0. It is vanished because it is the tangent is parallel to x-axis. Parallel to x-axis means what? It is 0. F dash of x1 is equal to 0. Understood? Or we can do like this. For example, the graph is, for example, if this is a graph, assume this is f of x graph. Now look at clearly at this point, assume it is x1. At x1, if we draw the tangent, x1 means this at this. So this is a tangent. So tangent is exactly parallel to x-axis, and this is one point. At this point again tangent is standing. Right? Tangent is standing. So therefore this tangent is parallel to exactly. Let's say this point is x2. At x2 also tangent is parallel, and here also at this point also tangent is parallel to x-axis. Let's say this point is some x3. So this point is some x3. And at this, again this is a tangent and this is parallel to x-axis, so let's say this is x4, and at this again it is parallel, so therefore at this point the tangent is parallel to x-axis. Therefore let's say this point is some x5 like this, and x6, the last point is x6. That means at this point, so at this point the tangent is parallel to x-axis. So therefore at x2, x3, x4, x5, xt, x1 to x6, x1, x2, x3, x4, x5, x6, all these points, the derivative is vanished. So f dash of x1 equal to 0 and f dash of x2 equal to 0 and f dash of x3 equal to 0. So up to so on, f dash of x6 equal to 0. So derivatives are vanishing, and here only I want to extend same thing. So the curve is like this, and it is a sharp peak. For example, this is a sharp peak. Now look at this point, derivative does not exist. Look at this point, there is a sharp peak, tangent will not stand here, right? It will fall either left side or right side. So therefore at this point, let's say this point is x0. At x0 derivative does not exist. That means what I can say here, so f dash at x0, what I can say here, does not exist because it is a sharp peak, derivative does not exist. Therefore such kind of points are said to be critical points. Those are said to be critical points. This is geometrical view. Same thing for this kind of function also, functions of two variables, which is a function of single variable. Same ideology for the functions of two variable. Now look at again an interior point of the domain. Look at these are interior point x0 to all these are interior points. Let's take the interval is 0 to some 10, for example. 0 to 10. In this intervals, these are the interior points, x0, x1, x2 up to so on, all these are interior points, right? So an interior point of the domain of a function where both fx and fy are 0, both are vanish, that means what, derivatives are vanishing, or where one or both of fx and fy do not exist, like this, like x0 point, it does not exist, right? Then such points are said to be critical points or stationary points. Indirectly, where the derivative is parallel to x-axis or parallel to y-axis here, or does not exist, fails to exist, then those points are said to be critical points. Okay. Now let's look at one theorem. First derivative test for local extreme values. Extreme means maxima and minima. Okay. If f of x and y has local maximum or local minimum value at an interior point a comma b of its domain, and if the first order partial derivatives exist there, where at a comma b, first order partial derivatives exist, that means fx and fy, these both are exist at a comma b. Okay, then fx at a comma b is 0 and fy at a comma b is 0. Just now I said f dash of x1, right? F dash of x1 equal to 0 means what? F dash at a1 is 0. That means what, derivative is tangent is parallel to x-axis. Same thing here. With respect to x, right, it is also derivative. Derivative at the point is 0. Similarly, derivative at the point a with respect in the y direction, that is also 0, because here two variables, so for both the direction we have to consider x and y directions. So in the x direction tangent vanish, in the y direction tangent vanish. Okay. So that is true when there is a local maxima or minima. That means geometrically it is like this. Same previous graph only, just look at, for example, if you are having this kind of graph. So clearly by observation, what is the maximum? So this is the maximum, right? This is maximum. Function value will take maximum at this point, and function value will take, so therefore the minimum value is at this point. So this is a minimum value, right? This is a minimum value, this is minimum value, at this point it is minimum. Okay, which point? At this point. At this point minimum occurs, and corresponding at this point maximum occurs. So this is maximum peak. That is called, it is maximum. So what the theorem says, if f of x and y has local maximum or local minimum value at an interior point a comma b of its domain, and if the derivative, first derivative, partial derivative exists there and they are vanish, at which point, let's say it is a comma b, so this is a comma b, at this point clearly, see, since I am looking for one dimensional, just it is for two dimensional, look at for one dimensional, at one dimensional, for example, if it is x1, at this point x1, f dash of x1 is 0, right? F dash of x1 is 0. So clearly, to attain maximum or minimum, for example, f dash of x1 is equal to 0, it means what? It is a sign for there is a maximum or minimum. That's it. For example, look at this point also, if you draw the tangent, it is 0. But at this it is maximum, at this it is minimum. But overall minimum is this. This is global minimum. Okay. So this is maxima. This is also one of the maximum. But in this maximum, which one is? So here also tangent is vanished. So in these three, look at here, here and here. At all these three places maximum occurs. In this the main global maximum is this one. So this is maximum, overall maximum, and this is local maxima, it is local maxima, it is local maxima, and this is, look at, this is local minima. Okay, this is also minimum value, this is also minimum value at this point. Okay, tangent does not exist. So where, again, that's what I said. So f dash of at some point, let's say it is some xn, if it does not exist, and there is a sign for maxima or minima, there is a sign for maxima and minima at that point. Why? Because look at, for this curve only, at this point derivative does not exist. So therefore, for example, if this point is xn, okay, now I can say that clearly without looking at the function, by looking at the graph, since at this point derivative does not exist, therefore at this point minimum occurs. Minima or maximum occur, we cannot say. For example, if the graph is like this, so if the graph is like this, for example, if this is a graph, clearly at this point, look at this point maximum occurs, right? at this point. But at this point derivative does not exist. So therefore I can say that f dash of, let's say it is some point xn. Let us consider this point is xn, this point is xn. So f dash of xn does not exist, right? Derivative does not exist. Does not exist. Now look at in these two cases. Here derivative does not exist, here also derivative does not exist, but here minimum occurring, it is maximum occurring. Therefore, just I can say that if derivative does not exist at some point x0, then it is an indication of at that point either maxima or minima occurs. Either maxima or minima occurs, where the derivative does not exist. Similarly, for tangent is equal to 0 also. Look at this point tangent is equal to 0, first graph. At this point tangent is equal to 0, but here maxima occurs, here minima occurs. So therefore, where tangent is equal to the 0, at that point again same story, maxima or minima occurs. Maxima or minima occurs. So same that theorem saying here. So if f of x comma y has local maximum or local minimum value at an interior point a comma b. Now I am looking at interior point only. Now we should not consider this kind of boundary points like xn kind of. Previous these two graphs. This xn we should not consider, and here x0 we should not consider because these are boundary points. Okay, only I am looking for interior points only. So at interior points, if the derivatives are vanished, that means at that point local maxima or local minima exists. So at this point, this is local maximum. This is local maximum. Look at, so this is local maximum, and this is local maximum, and this is local maximum, and all these are interior points. All these are interior points. And at this point, maxima occur, and at this point also maxima occur. So at this point, derivative is parallel to x-axis. So and this is also at these three places, local minima occurs. Global means what? Global means overall. Overall I can say this statement. So now let me write that statement. Overall statement is this. So overall statement is, let me write this graph is here. So let me write the graph is here. Same kind of graph. So maxima occur at this point, but at this point derivative does not exist. Minima occur at this point, but at this point derivative does not occur. Okay. So therefore, theorem number 2 now. Theorem number 2. Okay. Yeah. Look at this theorem. Theorem number 2. If fx, fy vanish means equal to 0. That means x derivative with respect to x and derivative with respect to r vanish, or does not exist at some point a comma b in the domain of f of x comma y, then at that point a comma b, f of x comma y should have extreme values. Extreme values means f of x comma y should have either maximum or minimum value. Look at this is the main thing. Note. Here a comma b can be boundary point or extreme point. Boundary point. That means at the end point. So therefore now indirectly we are looking overall interval from the starting to ending. From starting to ending, the derivative fx fy vanish or does not exist, then clearly I can say that at that point maxima or minima can occur. We are going to discuss about Lagrange's method of multipliers, which gives you the maxima and minima of a function, okay, particularly multivariable function. Okay, now let us enter into in details. Suppose that f is a function of n variables is given to us, and conditions are given, which are functions of again n variables. Pi I is running from 1 to k. So k constants are given, pi 1, pi 2, pi 3 up to so on k. All these are differentiable functions. What do you mean by differentiable? You know from PUC. So all these function and all these constraints are differentiable functions. So this is the first requirement. To find the maxima or minima of the function f here. So the function f subject to the constraints pi I x1 to xn, where I is running from 1, 2, 3 up to so on k. I is running from 1 to k, where this n is more than k. This number of variables are more than k. That means, for example, you are having a function f which is have two variables x1 comma x2, for example 3 variables x1, x2, x3. Then the number of constants should be pi 1, pi 2 only. Look at number of variables are 3 here, number of constants are 2, therefore 3 is more than 2, like this. Either you can take one constraint or you can take two constants, your wish. But after 2, maximum 2 only you can take. Okay, you should not take 3, you should not take 4. So number of constants should be allowed which are less than the number of variables. Okay, if the number of variables are 3, then the number of constants must be up to 2 only. So that is the requirement. Then methodology, look at of Lagrange's method of multipliers. First one, we construct an auxiliary function. We need to construct an auxiliary function. The auxiliary function is this one. So f of the capital F, I am defining capital F. This given function is small f. Look at small f. Now I am defining the capital F is number of variables are n, because given function having n variables. Look at small f having n variables. So x1, x2 up to so on xn, and since the number of constants are here k, look at pi i's are conditions, constraints. Therefore, how many they are? They are k. So therefore, k lambda k times lambdas I need to take, lambda 1, lambda 2 up to so on lambda k. If the number of constants are 3, you have to take 3 constants here, lambda 1, lambda 2, lambda 3, like that. Okay. Now this will be, it is defined like this. Given function f of x1 to xn, lambda 1 into first constraint, lambda 2 into pi to second constraint, lambda 3 into third constraint, up to so on lambda k into kth constraint. And this will be clubbed like this. F of x1 to xn plus summation I is running from 1 to k, lambda I, lambda pi I. If there are only 3 constants, then I is running from 1 to 3 you have to write. Okay. So this is about auxiliary function. We need to construct this one first in this methodology, where all these lambdas are defined undetermined parameters which are known as Lagrange's multipliers. All these are lambdas are said to be Lagrange's multipliers. Okay. Next, second point in the methodology. Yeah, what is the second point? To determine the critical points or stationary points of the defined function capital F, we have necessary conditions are this. For example, look at if you are having a one variable function. For example, look at this. So clearly by graph, this function having maxima at this point, right, minima at this point, for this particular function only, right, maxima at this point, minima at this point. So therefore, for example, this point is x1 corresponding, so this point is x1, their corresponding function value will be f of x1, right. Therefore f of x1 is the maximum value, and for example this point is x2 and corresponding function value will be f of x2. Therefore this is a minimum value. First I need to know what is x1, what is x2. So these are called critical points. So how to know these points? Look at this point, if you draw the tangent is parallel to x-axis. That means what? Indirectly f dash of x1 is equal to 0. That means what? This tangent is parallel to x-axis. And if you draw the tangent at this point, again this is parallel to x-axis. Okay, that means what? Again f dash of x2 is equal to 0. That means where the tangent are parallel to x-axis, at those points are set, at those points maxima or minima occurs, and those points are said to be critical points. That's what we explained in the last class already. So our goal is to collect what is x1 and x2. How to collect these points? Simply where the derivatives vanish. Same thing I am doing here. Look at where the derivative is vanishing. Since it is a single variable function, therefore I am writing df by dx, derivative means, because f is a function of single variable. But here capital F is a function of n variables. That's why partial derivatives will comes into picture. So therefore, dou f by dou x1 is 0, dou f by dou x2 is equal to 0, up to so on dou f by dou xn is equal to 0. So and all these togetherly will give us the critical points. Our main goal is what are the critical points. So once critical points are obtained, then substitute the points in the function, you will get corresponding function values. In that the highest one will be the maximum one and the lowest one will be the minimum one. So for example, x1, x2 is there. For example, x1 is 1, x2 is 2. For example, function is f of x is equal to x square plus 2x plus 1, for example, plus 2x plus 1. Okay, let's say. So then what I will do, once critical points are 1, then I will substitute in the function so that I will get function value here. So for example, 4. Next, 2 is the second critical point, therefore substitute here. What I will get? 9. So in this 9 and 4, which is highest? 9 is the highest. Therefore, this is a maximum. Like this I will conclude. And in this, 4 is a minimum. Therefore, this is a minimum value. That's it. So therefore, for this function, f maximum is 9, minimum is 4. Just roughly I am explaining, not actually maximum 9 and minimum 4. Just roughly I am explaining. Same story here. First critical points we need to obtain. After getting the critical points, we have to substitute back in the function so that we will get the function values. In that we will collect the maximum one, that is a maximum of the function. Then collect the minimum one, that is the minimum of the function. So that is the ideology. Okay. So critical points can be obtained by these conditions, these necessary conditions. Next, third point in the methodology, by solving the constraints are given to us, conditions, how many k's are given, k constraints are given, and these k constraints, just now we computed dou f by dou x1 is 0 and dou f by dou x2 is equal to 0 up to so on, dou f by dou xn is equal to 0. Take all these things. So all these things with including constraints, you solve it, then we will get critical points. What are the critical points? Critical points are nothing but x1 to xn. So once critical points are obtained, then the next point is, at all these critical points, including boundary points of f, boundary points, f can attain its extremum. What I want? Compulsory critical points I want. Okay. Now let us look at few problems. That will be very clear. Now look at this. What do you want? Find the maximum and minimum values of the function f of x comma y of this, and on the circle this. On the circle only we have to find the maximum or minimum. See, for example, if you look at the one variable case, for example, if this is my function, so let's take this point is some 1 and this point is some 2, this is 3 and this is 4. So now I am looking for 1 to 4 only. In the interval 1 to 4 only, what is the maximum and minimum? Only 1 to 4. Between 1 to 4 means from here to here only. Here to here only I want to look at the maximum and minimum. Now, so clearly at this point the tangent is parallel. Understand? At this point the tangent is parallel. Then what I have to do? So therefore, so at this point the tangent is parallel. This point is nothing but 3. Therefore 3 can be critical points. And at this point also tangent is parallel. And what is this point? 1.5. Let's take that is 1.5. Now at these 2 points I need to compute the function values. Then corresponding maximum and minimum I will get. So before that, look at in this interval 1, 2, 3, 4, all these are domain points. Corresponding function values, for example, 1 is a domain point. Now what is this? This is f of 1. This is a range point. And 3 is this. Therefore corresponding function value is f of 3. This is range point. Likewise. So these are domain points. Corresponding range value should be on the curve only. Right. Same thing here. So now this is the function. Okay, let's call it 1. So let me draw that rough figure. Not exactly, just for understanding purpose. Okay, now this is 3x plus 4y. Let us consider just 3x plus 4y. Now for this function, where I have to do? I have to find the maxima and minima in this circle only. In this circle only. Okay, now we should not cross this circle. So now within the circle, how many points are there on the circle? Infinitely many points. Similarly, how many points are there in this interval 1 to 4? Again, infinitely many points. 1, 1.1, 1.2, likewise. Infinitely many points are there in this interval. Similarly, infinitely many points are there on this circle. Now, for example, at this point the tangent is parallel, and at this point the tangent is parallel. That what I mean to say is these 4 points are critical points. For example, okay, this is domain, right? Here, like what I said, 1.5 and 3 are critical points which are in the domain. Similarly, these 4 points are critical points which are in the domain. Now, corresponding function values. For example, at this point, this is a function value. And at this point, this is a function value. At this point, this is a function value. And at this point, corresponding, this is a function value. Look at 1, what is the function value? This is function value f of 2. Same story here. So, at this is a function value. So, all these function values we need to obtain. Then, in that, we have to look at maximum 1 and minimum 1. That will be the maximum and minimum. So, this is the ideology. Okay. Now let us enter into in details. So by Lagrange's method of multipliers, by Lagrange's method of multipliers, so what is the first point in this? The first point is we need to construct auxiliary equation, right? So now auxiliary equation. So before entering into auxiliary equation, I want what is f of x comma. So here two variable function f of x comma y, x1 comma x2 kind of, okay? F of x comma y, which is, what is that? 3x plus 4y. 3x plus 4y. Now how many constants are given? Only one constant. Therefore I am writing pi 1. What is pi 1? pi 1 is nothing but x square plus y square minus 1. Bring this 1 to left hand side, so minus 1. So this is a constraint. Now construct auxiliary equation now. Since it is a function of two variables, therefore f of x comma y. How many constants are there? Only one. Pi 1 is only one constraint. Constraint is nothing but condition. So indirectly domain. Okay, there is a domain boundary or domain condition indirectly. So therefore lambda 1, right? How many Lagrange multipliers we have to take? Only one, because one constraint. So therefore Lagrange multiplier is only one, that is lambda 1. If there are two constraints, then take two Lagrange multipliers, lambda 1 and lambda 2. Now what is this? So this is nothing but 3x plus 4y. Okay, 3x plus 4y plus lambda 1 into pi 1. Lambda 1 into pi 1. That means 3x plus 4y, 3x plus 4y plus lambda 1 into, and the constant is x square plus y square minus 1. So this is the given auxiliary function. So this is first point of the Lagrange multipliers. First point is over. Next second point. What is the second point? Second point is, yeah, now you want critical points, right? Critical points. That is about second point in the methodology, critical points. How to collect critical points under the sufficient conditions? Dou f by dou x1, dou x is 0 and dou f by dou y is equal to 0, because there are two variables. So therefore what I want? Dou f by dou x1 equal to 0 actually. Okay, and dou f by dou x2. But here instead of x1 you are having x, instead of x2 you are having y. So these two you have to solve. Then you will get the critical points. First of all, let us construct what is these two. Dou f by dou x1 and dou f by dou x2. Okay, now let us write. So first, what is capital F? Let me write. Capital F is x comma y comma lambda 1, which is 3x plus 4y, 3x plus 4y plus lambda 1 into x square plus y square minus 1. Okay, now what I want? Dou f by dou x. First I am collecting what are the critical points. Okay, is equal to 0. That means what is dou f by dou x1? With respect to x you have to do the derivative, therefore it is 3. Okay, 3 plus lambda 1 times with respect to x, therefore 2x only, and this is exactly equal to, assume this is 1, equation number 1. Okay, next second one, dou f by dou y is equal to 0, because it is a two variable function. Next, what is dou f by dou y? 4 plus lambda 1 into, with respect to y, so 2y, which is equal to 0, and assume this is number 2. Okay. Next, what is the third point in the methodology? The third point in the methodology is we need to solve, we have to solve equations 1 and 2 with constraint, right? With constraint. That is third point. Look at, with constraint pi 1, because only one constant here, pi 1. So which is nothing but what? X square plus y square minus 1. So you have to solve these two equations including constraint for what? For critical points. For critical points or stationary points. For critical points. What are the critical points? Are x comma y only, because it is a two variable function. So now let us solve those. Okay, so constraint, what is constraint here? X square plus y square is equal to 1. Okay, now, and in this, from this you collect what is x, what is y, and substitute here, so that you will get the lambda 1 value. So therefore equation number 1 implies, what is x now? So x is equals to, from here x you write down, minus 3 by 2 lambda 1. Okay, next what is y value? So from 2, so equation number 2 implies, okay, yeah, so equation number 2 implies what is lambda, what is y? So y is equals to minus 4 by 2 lambda 1, 4 by 2 lambda 1. Okay, so now let us take this constraint, let us take this is number 3. Okay, now substituting 3, so therefore 3 implies, our main goal is to find what are the stationary points x and y. For that we are solving this 1 and 2 including constraint. That's what I am doing actually. So now 3 implies x square plus y square is 1. So x square plus y square is equals to 1. Okay, that means what is x square now? Minus 3 by 2 lambda 1 whole square. My ideology is why I am substituting here. That is also very clear. So if I substitute here, I will get lambda 1 value because only one unknown lambda 1. Once I am getting lambda 1, then I will substitute in equation number 1 and 2, so that I will get x value and y value. Once lambda 1 is known, I will substitute here so that x1 y value can be obtained. So that is my ideology. So now, yeah, what is this? 9 by 4 lambda 1 square. Okay, plus 16 by, is it 4 lambda 1 square is equal to 1. So total, what is it? 25 by 4 lambda 1 square is equals to 1. So therefore clearly, what is it? Lambda 1 square is 25 by 4. Okay, so lambda 1 square is 25 by 4. So lambda 1 square is 25 by 4. So that means what is lambda 1 now? So lambda 1 is square root over 25 by 4. That means you will get plus or minus 5 by 2. So having 2 lambdas, so then corresponding x values. So now, yeah, let us find all those values. So for lambda 1 is equals to plus 5 by 2. Okay, then corresponding x value and y value we have to compute. Okay, now from 1 implies, okay, equation number 1 implies, so what do you have in equation number 1 and 1? So equation number 4 and 5, right, this is 5, right, this is 5. Okay, so from 4 and 5, equation number 4 and 5, what is equation number 4 says? So x value is x, right, not x1, it is x value. So x value is so x is equals to minus 3 by 2 lambda 1, right? Now what is this? Minus 3 by 2 into lambda 1. Lambda 1 is 5 by 2. I am taking plus 5 by 2 first. So 2 is out, you will get minus 3 by 5. So x value is minus 3 by 5. Okay. Next equation number 5 implies, yeah, what is y value? Y value is minus 4 by 2 lambda 1, isn't it? Check once. Now this is minus 4 by 2 into, what is lambda 1? 5 by 2. Okay, again 2 is out, you will get minus 4 by 5. So therefore, what I got the point now? So now the point is, so x comma y is minus 3 by 5 comma minus 4 by 5. Okay, or you can carry it like this, instead of doing like this, yeah, let us drop this thing here, plus or minus 5 by 2. Okay, so here plus or minus 5 by 2, right? So once you are writing here plus or minus 5 by 2, here also plus or minus 5 by 2. What will you get here? Here also plus or minus 3 by 5. Okay, here minus or plus, because your minus is there, so minus or plus 3 by 2. Okay, okay, so what I say here, minus or plus 3 by 5, and here again say minus or plus 3 by 5. So minus or plus 3 by 5. So that means what you are having, x is having, so therefore what is having, x is minus or plus 3 by 5 and y value minus or plus 4 by 5. So critical points are x and y only. So therefore finally the critical points are critical points. You have to write all those combinations here. Okay. Write the critical points here. So first critical point is, first you take x is plus. So plus 3 by 5 I am taking. And y is also plus. So 4 by 5. Next, let us take x is minus. So minus 3 by 5. And y is plus 4 by 5. Okay. Because here plus or minus, total 4 combinations will come. Next here x is positive is over, x is negative is over. Next, y is negative I have not taken. So 3 by 5 and y is negative, minus 4 by 5. Next, both are negative combination. So minus 3 by 5, isn't it? And minus 4 by 5. So all the combinations I have taken. So these are the critical points. And at these points, I need to find out what is the function, what are the function values. In that, maximum one and minimum one we have to collect. Okay. So first critical points are over. Next, fourth point of the methodology. Let me write here itself the fourth point. Yeah. So fourth point of the methodology is extreme values. Okay. Extreme values. Yeah, let us come to the extreme values. First, what is f of x comma y? So f of x comma y is 3x plus 4y. Okay. Now f of all the critical points is substituted. First critical point is 3 by 5, 4 by 5. So 3 by 5 comma 4 by 5. So add this, what is the function value? So 3 into 3 by 5, right, plus 4 into 4 by 5. What will get? 9 plus 16, 25 by 5. So answer is 5. So at first critical point, the value is 5. Next, at second critical point, now what is second critical point, which is minus 3 by 5, comma 4 by 5. I am substituting in the function. What will get? So 3 into minus 3 by 5, 3x, right, 3x plus 4y. So 4 into 4 by 5, 4 into 4 by 5. Now what will get? Minus 9 by 5, right, plus 16 by 5. So what will we get? 7 by 5, right, which is 7 by 5. 7 by 5, it is 1 point, it is 1.4, 1.4. Next, at third critical point, f of 3 by 5, right, comma minus 4 by 5. What is the function value now? So 3x, 3 into 3 by 5, 3 into 3 by 5, plus 4 into minus 4 by 5, minus 4 by 5. What do you get? So minus 9 minus 16, so minus 16, right, it is. So what about here? 16 plus 9, 25, yeah, correct. Yeah, 9 minus 16, so minus 7. Minus 7 by 5. So minus 7 by 5, again it is minus 1.4. And the next last one is, last critical point, minus 3 by 5 and minus 4 by 5. Add this, what is the function value? So 3 into minus 3 by 5 plus 4 into minus 4 by 5. That is what? Minus 25 by 5, minus 25 by 5. That means what? Minus 5, minus 5. Now look at in this. So first function value is 5, next function value is 1.4, next minus 1.4, next minus 5. So in this, what is the maximum one? Maximum is 5. So therefore this is called maximum of the function. So maximum of the function 3x plus 4y within the circle of domain is 5. And in this, what is the minimum one? The minimum one is minus 5. So this is the minimum one. So therefore minimum is minus 5. So minimum is minus 5. That's it. So this is a conclusion. So maxima and minima. Similarly, second problem. Yeah, look at this. Find the minimum value of the function. Only minimum value is asking. Only minimum value. Okay. Of the function x square plus y square plus z square subject to the conditions x into y into z is equal to a cube. So therefore here the function is f of x comma y comma z. The three variable function is given to us, which is x square plus y square plus z square. Okay, and constraint only one is given, that is x into y into z minus a cube. Okay, so therefore by Lagrange's method of multipliers, I am writing LMM, Lagrange's method of multipliers. I need to construct the auxiliary equation, right? First point is auxiliary equation. So what is that? F of x comma y comma z, three variable, and how many constants? Only one. Therefore one Lagrange's multiplier, lambda 1. So which is nothing but x square plus y square plus z square plus lambda 1 into pi 1. Okay, now this is nothing but x square plus y square plus z square plus lambda 1 into what is the constant? X, y, z minus a cube. This is auxiliary equation. And the second point, we want critical points, right? So for that, sufficient conditions we have to impose. So second point is for critical points. What I have to do? Dou f by, since it is three variable function, so 3 will be there. Dou f by dou x equal to 0. So that implies, directly I am writing. So what is dou f by dou x now? So 2x, with respect to x you have to do derivative. This lambda 1 is outside and inside with respect to x, therefore y into z. That's it. Is equal to 0. Next, similarly, dou f by dou y is equal to 0. Dou f by dou y. So if you impose this, what you will get again? With respect to y, therefore 2y plus lambda 1 into with respect to y, therefore xz equal to 0. And last one is dou f by dou z. Dou f by dou z, which is equal to 0, which is implies with respect to z, therefore 2z plus lambda 1 into with respect to z, therefore x into y equal to 0. So now these three we have. So let us write this one equation number 1, and this is equation number 2, and this is equation number 3. What is the third point in the methodology? We have to solve. So third point in the methodology, third point is we have to solve equations 1, 2 and 3 with the constraint, right? With the constraint. What is that? X, y, z is equal to a cube. So with this constraint we have to solve it. So then write equation 1, 2, 3. So equation number 1 implies, so 2x plus lambda 1 into yz equal to 0, right? And equation number 2 implies 2y plus lambda 1 into xz equal to 0. And equation number 3 implies 2z plus lambda 1 into xy equal to 0. So we need to observe carefully here, and we have to utilize this constant x into y into z is equal to a cube. Okay. So look at the from the first one. So here from this equation, okay, what is lambda 1 into yz? Lambda 1 into yz is minus 2x. Okay, and from this lambda 1 into xz is 2y, minus 2y. Okay, minus 2y. And from this, and lambda 1 into xy is how much? Minus 2z. Again, I want to more elaborate, and from this again, from this lambda 1, or simply lambda 1 into xyz value, how much? Simply I am multiplying both sides with x, so minus 2x square. Okay, and here lambda 1 into xyz again I am multiplying with y, so minus 2y square, and here I am multiplying both sides with z, so lambda 1 into xyz, what will get? Minus 2z square. You may get out why I am multiplying all these things, because look at the constant x into y into z is there, I may use a cube value here. Okay, so therefore again, so that means from here, okay, lambda 1 into, so therefore xyz value, so therefore from this x into y into z value is equal to minus 2x square by lambda 1, right? Next, again from second equation, x into y into z value, so from this equation x into y into z value minus 2y square by lambda 1, again x into y into z value minus 2z square by lambda 1. So what you understood, all these are xyz only, therefore all these three must be equal. So therefore all these three I can write as minus 2x square by lambda 1 is equals to minus 2y square by lambda 1 is equals to minus 2z square by lambda 1, isn't it? So minus 2 by lambda 1, 2 by lambda 1, minus 2 by lambda 1, everything will be cancelled out, then you will get x square is equal to y square is equal to z square. Therefore all the values are equal, x square, y square, z square values are equal, and with the constraint our main goal is what is xyz, that's it. Whatever the struggle you can do it, but you will find xyz, which is critical point. With the constraint, what is the constraint? X into y into z is equals to a cube. So this is the constraint. Okay, so therefore clearly, so now can you give xyz such that it satisfies this equation, so that if you multiply 3 you will get a cube. Can you give what is a, what is x, what is y, what is z? All three must be equals. Look at, all three must be equals, and if you multiply you will get a cube. Therefore x must be a, y must be a, z must be a. X must be a, y must be a, z must be a. So that a into a cube, isn't it? If I take x is minus a, y is plus a, z is minus, again a cube I will get, right? So therefore the possible values for x, y, z are, I can take, listen carefully, x value, so therefore critical points, let me write the heading critical points. Therefore critical points are, I am writing critical points. Okay, yeah, look at by observation, critical points are, first I am writing a, next y is also a, z is also a. Now substitute x into y into z, you will get a cube. I am getting a cube. Why I am choosing a, because okay, because of this one, I got x square is equal to y square is equal to z square I got. So therefore these points will satisfy this condition also. Next, not only that, if I choose x is minus a, y is plus a, z is minus a, this is also will satisfy. Look at a cube, and here also a square, a square, a square, and here you choose a, and here minus a, and this one is minus a. I can choose this also, right? And next minus a, and a, and these also will satisfy. See, look at whatever the struggle you do it, but finally I want what are the critical points. That means what are x, y, z. So x, y, z, x, y, z are critical points. Use these three conditions. Which one? The partial derivative fx is equal to 0, fy is equal to 0, fz is equal to 0. That means dou f by dou x, dou f by dou y, dou f by dou z. The three equations you use, and the constraint you use. Total 4 equations you are having. Use these 4 equations in whatever the way, but find out what are x, y, z. So that is the ideology actually. So this much I struggled for getting this x, y, z. So now four points we are having, critical points. Now at these points, what is the function value I need to compose? I need to find out. Okay. Now the function value at those points, Therefore, what is the function now? F of x comma y comma z. F of x comma y comma z is, which is x square plus y square plus z square. Now, at critical points, what is the function value? F of a comma a comma a. What is this? A square plus a square plus a square, which is 3a square, which is 3a square. Okay. Next, f at minus a and minus a. At this point, again same story, 3a square only will get because squares are there. So therefore, next f of a comma minus a comma minus a. At this point, what is the function value? Again 3a square only. Okay. And f of minus a comma minus a comma a. At this, what is the function value? Again 3a square only. But every time I am getting only 3a square only. But what I want minimum value. But is it minimum or maximum? How to decide? Okay, 3a square I got, perfect. But is this a minimum or maximum? We don't know, right? Because at critical points, maxima or minima occurs. I cannot say particularly which one maximum, which one minimum, unless if you know the function value. That's why in the first problem, critical points I got, then I substituted in the function. I got few values, plus 5, next minus 5 and minus 1.2 plus 1.2. In that maximum one I have taken, maximum is 5, therefore that is a maximum. But here 3a square I got, only one value 3a square I got, but this is a maximum or minimum, we don't know. Now we have to decide is a maximum or minimum. Now for that one logical thing I want to proceed. See, what is the arithmetic mean of x square, listen carefully, x square, y square, z square. What is the arithmetic mean of x square plus y square plus z square, which is x square, sum of observations, right? X square plus y square plus z square by number of observations is 3. Yes or no? For example, what is the mean of 1, 2 and 3? Average. Mean is nothing but average or arithmetic mean, whatever. 1 plus 2 plus 3 by sum of observations by number of observations, right? So 6 by 3. So you are getting 2. So this is the average. Average is 2. Same story I am doing. Arithmetic mean of 3 numbers. First number is x square, second number is y square, third number is z square. Its mean is sum of observations divided by number of observations. Fine. Next, geometrical mean. What is geometrical mean? Geometrical mean of x square, first number, y square, second number, z square is third number. What is the geometrical mean of this? Since 3 numbers are there, therefore cubic root of product of those numbers, right? X square into y square into z square. This already have seen in PUC. Geometrical mean. For example, 3 comma 1 comma 4 is 3 numbers. What is geometrical mean? Since there are 3 numbers, therefore cubic root of 3 into 1 into 4. This is geometrical mean. For example, let us write 1, 4, 2, 3. How many numbers? 4 numbers. Therefore, what is the geometrical mean? 4th root of your, right? 4th root of product of numbers. 1 into 4 into 2 into 3. So this is geometrical mean. Same like I have taken 3 numbers. What is geometrical meaning? Cubic root of x square, y square, z square. Now in general, which is more? Arithmetic mean is more or geometrical mean is more? Obviously arithmetic mean is more, right? So therefore in general arithmetic mean is more than or equal to geometrical mean. You take any numbers and you try, definitely arithmetic mean is more than or equal to geometrical mean. Now it means, what does it mean now? So this is, what is arithmetic mean now here? X square plus y square plus z square upon 3. And this is more than or equal to geometrical mean. Cube root of x square into y square into z square. Okay, it means, yeah, let me simplify here itself. So x square plus y square plus z square is more than or equal to 3 into x square y square z square whole to the power of, what is this, 1 by 3, right? Whole to the power of 1 by 3. Now this will be, yeah, let me write here itself. Yeah. and this will be, right, yes, so this will be x square plus y square plus z square, right, which is more than or equal to 3 times x into y into z whole square, right, whole square but power 1 by 3, so 2 by 3 I can write, isn't it? Now this is x square plus y square plus z square is more than or equals to 3 into, what is x by z value? X into y into z value, look at the constant, x into y into z is how much? A cube, right? So this is a cube, right, instead of x into y into z, a cube 2 by 3. Why a cube? Because constant, look at the constant, x into y into z is equal to a cube, so I am using that constraint. Now, so 3 is out here, so 3 is out, you are getting 3a square. So finally what I got, x square plus y square plus z square is more than or equals to 3a cube, 3a square, sorry, cube is cancelled, power 2 is there, so 3a square. Now look at, this is my function actually, x square plus y square plus z square is nothing but my function, right? Look at f of x comma y comma z is my x square plus y square plus z square. Therefore f of x comma y comma z is more than or equals to 3a square. What does it mean? 3a square will be the lower bound, so therefore this will be the minimum, so therefore this 3a square will be the minimum, so it is not maximum. So to decide it is a minimum, we have struggled, okay, just to decide whether it is a maximum or minimum, that's it. So by this logicness we got this is a lower bound, therefore it must be a minimum, therefore 3a square will be the minimum of the function f of x comma y comma z, x square plus y square plus z square under the condition constraint x into y into z is equal to a cube. That's it. Okay, next look at this, I will give the hint, you do it again. Same here, how many constants are there? So therefore let us construct the auxiliary equation, x into y into z is equals to what is this, 2x plus 3y, 2x plus 3y plus z. Okay, how many constants? 2 constants plus lambda 1 into first constant x square plus y square minus 5, okay, and second constant lambda 2 into x plus z minus 1. So this is auxiliary equation. Next we proceed for critical points. So dou f by dou x equal to 0 and dou f by dou y equal to 0 and dou f by dou z equal to 0, and we get 3 equations. These 3 equations including these 2 constraints, total 5 you are having, solve it for x, y, z, you will get critical points, then find corresponding extreme values, that means maxima and minima. The answer is, I will give the answer, you try once. One minus 5 into root 2, and second value will get 1 plus 5 into root 2. Okay, so in this 2, which one is maximum? So this is the maximum, therefore this is the maximum value. Okay, and this is the minimum value. Only 2 critical points will get, at the 2 critical points these 2 function values. Okay, try with this same ideology, and with this our 5th unit is closed.